Close your eyes. Picture yourself on a pristine beach, the sun warm on your skin, the rhythmic lull of the ocean lulling you into serenity. A perfect paradise, isn't it? Now imagine that serene scene shattered. Imagine a wall of water, taller than any building you've ever seen, rising from the calm blue horizon. Imagine the deafening roar as it engulfs the beach, swallowing the sand, the palm trees, everything in its path. Have you ever pondered the raw power of a tsunami, an oceanic leviathan that can obliterate coastlines? This awe-inspiring force is not birthed from the sea itself, but rather from the restless stirrings of our planet's crust. Let's embark on a journey beneath the Earth's surface to discover the geological genesis of tsunamis. At the heart of this phenomenon is the ceaseless movement of tectonic plates, the colossal jigsaw puzzle pieces that comprise the Earth's lithosphere. Imagine two of these behemoths converging at the bottom of the ocean, locked in a silent struggle of titanic proportions. The heavier plate, laden with dense oceanic crust, is forced to retreat, sliding beneath its lighter continental counterpart in a process known as subduction. Subduction zones are the birthplaces of some of the most powerful earthquakes known to humankind. But what transforms an undersea earthquake into a tsunami? The answer lies in the displacement of water. As the subducting plate dives into the Earth's mantle, it drags a portion of the overriding plate along with it, causing the seafloor to warp and deform. When the strain becomes too great, the overriding plate springs back, releasing pent-up energy in the form of an earthquake. This sudden seismic jolt lifts the ocean floor, displacing an enormous volume of water above. In response, the ocean's surface rears up in a series of waves, racing away from the epicenter at high speeds. These waves, undetectable in the open ocean, grow in height as they approach the shallows of the coastline. Their energy, initially spread over a vast depth, is compressed into a smaller vertical space, causing the waves to rise up in a wall of water. And thus a tsunami is born. This process, from tectonic clash to oceanic onslaught, is a testament to the dynamic nature of our planet. It reveals the intricate interconnectedness of Earth's systems, where the shifting of rocks, miles beneath the ocean surface, can unleash a force capable of reshaping landscapes in mere minutes. So tsunamis are born from the Earth's ceaseless dance, a ballet of tectonic plates beneath the ocean floor. How does a mere ripple transform into a maritime monster? This question, seemingly simple, unravels a complex web of physics that underlies the propagation of tsunamis. In the vast, deep ocean, tsunamis are hardly noticeable. These waves, born from seismic disturbances, travel across the ocean floor at jetliner speeds, yet their surface manifestation is subtle. But as they near the shallower coastal waters, they undergo a remarkable transformation. The key to understanding this transformation lies in the principle of wave shoaling. Imagine a marching band, all in step, striding onto a progressively narrowing path. As the path narrows, the band members bunch up, maintaining their forward momentum, but crowding closer together. The same thing happens with our tsunami wave. As the ocean floor rises towards the shore, the wave's energy has less water to spread across, causing it to bunch up, or shoal, increasing the wave's height. But what about the energy that propels this wave? The conservation of energy principle holds the answer. The energy of a wave is distributed over its wavelength and amplitude. In deep water, a tsunami's wavelength is long and its amplitude is small. But as the depth decreases, the wavelength shortens, and to conserve energy, the amplitude or height must increase. This interplay of energy conservation and wave shoaling explains the monstrous transformation of tsunamis. In deep water, the tsunami's energy is spread out over vast distances, rendering the wave almost imperceptible. But as the tsunami approaches the shore, the ocean's decreasing depth forces the wave's energy to concentrate in a smaller vertical space. This energy compression leads to the towering heights that tsunamis are notorious for. And so, we find that the seemingly placid ocean depths play a crucial role in shaping the formidable force of a tsunami. The ocean's depth, thus, dictates the tsunami's height, turning a ripple into a rampaging wave. How can we predict these unpredictable sea serpents, you may wonder? Well, let's delve into the fascinating world of technology that allows us to do just that. Firstly, we have seismometers, the sentinels of the Earth's rumblings. When tectonic plates decide to dance, seismometers pick up their movements, detecting the seismic waves that radiate from the earthquake's epicenter. By measuring the magnitude and location of these quakes, seismometers provide the initial alarm, hinting at a potential tsunami. However, an earthquake doesn't always mean a tsunami. That's where deep ocean assessment and reporting of tsunamis, or DART buoys, come into the picture. These oceanic watchdogs sit patiently in the deep sea, keeping a watchful eye on the water column height. Any sudden or significant change in sea level could indicate a tsunami's birth. Once this change is detected, the DART buoys relay the information to satellites, which then transmit it to tsunami warning centers around the globe. Yet knowing a tsunami is coming isn't enough. We need to know where it's headed and the potential impact. This is where computational modeling takes center stage. By crunching numbers and simulating scenarios, these models predict a tsunami's path, speed, and destructive power. They take into account a myriad of factors, from the bathymetry of the ocean floor to the coastal topography. This information is paramount in issuing accurate and timely warnings to those in the tsunami's predicted path. But, like any scientific endeavor, it's not foolproof. Predicting tsunamis remains a challenging task due to the complexity of the ocean and the unpredictability of tectonic activity. Yet every detection, every prediction helps us refine our models, improve our technology, and better our understanding of these formidable forces of nature. Armed with technology, we strive to predict and prepare for these oceanic onslaughts. And while we may not be able to prevent tsunamis, we can certainly aim to minimize their impact through the power of prediction. What marks does a tsunami leave on our planet? A question that echoes in the minds of geologists worldwide. Tsunamis, these colossal waves of energy, are not just fleeting phenomena. They etch a distinctive signature into the Earth's geological tapestry, a signature that tells a story of power and transformation. When a tsunami strikes, it doesn't merely wash over the land. Rather, it reshapes the very contours of coastlines. Imagine the force of a wave several meters high, carrying the weight of the ocean behind it. The impact is so profound that it can shift sand dunes, erode cliffs, and even reshape entire islands. The coastline is left forever changed, a testament to the tsunami's raw power. But it's not just about reshaping. A tsunami also leaves behind a geological fingerprint in the form of sediment layers. As the wave recedes, it deposits a layer of sediment, a mixture of sand, silt, and marine microfossils. This layer, often distinct from the layers above and below it, serves as a silent witness to the tsunami event. By studying these layers, scientists can piece together the history of past tsunamis, giving us insights into their frequency and magnitude. Yet, the geological impact of a tsunami extends beyond the immediate coastline. The immense energy it releases can trigger other geological events like landslides. These landslides, both undersea and on land, can in turn generate their own tsunamis, creating a cyclic pattern of geological events. It's a stark reminder of how interconnected our planet's geological processes are. Scientists dedicatedly study these geological signatures. Through careful analysis of sediment layers, examination of reshaped coastlines, and investigation of triggered events, they strive to understand the intricate dynamics of past tsunamis. Each discovery, each tiny piece of evidence, adds to our understanding of these formidable sea giants. A tsunami, though transient, leaves a lasting imprint on our planet's geological narrative. It's a story told in the language of Earth itself, a tale of power, resilience, and constant transformation. The geological signature of a tsunami is not merely a record of past events, but a key to understanding our planet's future. How might our changing climate shape the future of tsunamis? This question propels us into the heart of our discussion today. As we grapple with the realities of climate change, we must also confront its potential impact on seismic oceanic events, specifically tsunamis. Rising sea levels, a direct consequence of our warming planet, may be a significant factor in the future frequency and intensity of tsunamis. As the oceans swell, the energy required to trigger a tsunami can potentially lessen, leading to an increase in these devastating occurrences. Think of it this way: the more water there is, the more there is to displace, and displacement is the primary catalyst of a tsunami. Simultaneously, changing ocean temperatures could play a role in the power of these seismic sea waves. warmer waters could potentially fuel more intense tsunamis, transforming them into even more destructive forces. Picture the ocean as a pot of water on a stove. The hotter it gets, the more it bubbles and roils, with the potential for overflow increasing. The implications for coastal communities are profound. Many of these regions are already grappling with the consequences of rising sea levels, from flooding to coastal erosion. Add the threat of more frequent and intense tsunamis into the mix, and it becomes clear that these communities face an increasingly precarious future. Yet, it's not all doom and gloom. Understanding the potential impact of climate change on tsunamis is the first step towards mitigating their effects. Continued research into this correlation is crucial, and so too is the need for preparedness. Coastal communities must be equipped with the knowledge and tools to respond effectively to tsunamis, from early warning systems to comprehensive evacuation plans. The reality is clear. As our climate changes, so too does the face of tsunamis. It's in our hands to understand, prepare, and adapt. Our changing climate presents us with new challenges, but with knowledge and preparedness, we can face them head-on. Let's take a moment to remember some of the most devastating tsunamis in history. These events serve as stark reminders of the raw power of nature and underscore the importance of understanding and preparing for tsunamis. Our first stop is December 26, 2004. The Indian Ocean tsunami, triggered by the third largest earthquake ever recorded, claimed over 230,000 lives across 14 countries. The waves, reaching heights of over 30 meters in some places, caused destruction on an unprecedented scale. We then travel to March 11, 2011, to the eastern coast of Japan. The Tohoku tsunami, precipitated by a 9.0 magnitude undersea earthquake, resulted in over 15,000 deaths. The tsunami also triggered the Fukushima nuclear disaster, causing a nuclear meltdown with lasting effects that we are still grappling with today. Finally, we journey back to November 1, 1755, to Lisbon, Portugal. The Lisbon earthquake and tsunami is estimated to have killed between 10,000 and 100,000 people, making it one of the deadliest in recorded history. The earthquake, followed by a tsunami and fires, virtually destroyed Lisbon and was felt as far away as Brazil. These events remind us of the raw power of nature and underscore the importance of understanding and preparing for tsunamis. As our climate changes, the stakes only get higher. Thank you for joining us on that thought-provoking dive into tsunami science. Do like this video and subscribe to SciSips for more science videos.